Heyo! Hello. Thank you for watching this geometry video. I hope all of you are doing well on this fine Friday. Is it afternoon? I don't know. Friday day. Anyways, we're moving on to 10.4. We're going to talk about these two special lines that exist around a circle. A secant line and a tangent line. Now, first we'll start with the definitions then. Here, I've drawn a circle for you. Notice you have a center there. A secant line is just a line that intersects a circle at 2 points. So that's what a secant line is. Lines that intersect a circle at 2 points. Here we have a secant line. It intersected at these 2 points. And a tangent line is just a line that crosses or intersects a circle at 1 point. So this is a tangent line. It intersects it here. And yeah, they intersect circle at 1 point. That point has a special name. That point's called the point of tangency. Now, there's some important things about this point. We'll get into that here in a bit, but some things to keep in mind. A secant line will always have an external part. The external part is the part that's outside of the circle, and it'll also have an internal part. So we could cut this secant line off at these 2 points. We could do that. And then the secant line would be this line that has the external part. It could end. It doesn't have to be a line. It could be a segment. It could end there. And this would be the external part. And then this would be the internal part. Well, the internal part is a chord, right? And so that's just something to keep in mind. The tangent line, it could be on both sides of this point of tangency. It doesn't have to go on forever. The tangent line could stop here. It could stop at the point of tangency as well. The tangent line is always external to the circle. There's only 1 point that's on the circle, and that's the point of tangency. Okay, here's a postulate for you. Ooh, wind's about to blow my stuff down. It's a postulate for you. The radius, so if this is a tangent line, right? If you draw a radius from the center to the point of tangency, that radius will always be perpendicular to the tangent line. So radius to the point of tangency is perpendicular to the tangent line. That happens all the time. And so if you have a tangent line, there's some information that's sort of built into that. Namely, this information. You could draw a radius from the point of tangency to the center, and it will be perpendicular to the tangent line. And so, one, you could say it this way as an if-then statement. If it's a tangent line, then the radius is perpendicular to the tangent line at the point of tangency. The reverse of that is true as well. So, for example, if you had a radius, like this is a radius, is it not? If you had a radius that's perpendicular to some external line, let's just call this line L. If you already know it's perpendicular, then what can you conclude? What can you conclude? That's hard to say. You could conclude that this line is a tangent line. And so what? If it's perpendicular, then it's a tangent line. Or if it's a tangent line, then it's perpendicular. And so these two things are things you will use. All right. Next, I got a theorem for you. It's called the two-tan theorem. The two-tangent theorem. If you have two tangents that are on the same circle, notice this line here, AB, this segment, it is a tangent line. It's only intersecting the circle at 1 point, and that's A. CB is a tangent line. It intersects the circle at 1 point, and that's point C. Notice both of these lines here, they share an external point. They intersect at the same external point B. If you have this scenario, if AB and BC are tangent lines, and they intersect at the same external point, then what could you say? Then those tangent lines are congruent. Oh, hopefully you can see that. Then those tangent lines are congruent. And so this happens every single time, and I'll show you why. Let me draw these two radii. 2 points make a line, right? So I could draw any 2 points I want, or any 2 lines I want. There we go. So these have the same value. I'll call it R. And I could also draw a line here from the center. Let's call it O. From the center O to B. Notice I have two triangles. And let me just kind of like fill those in just so you could see them. I've got two triangles. All right. Now, I'm going to explain to you why these two green lines, the secant lines, are congruent. Isn't OB congruent to itself, right, by the reflexive property? And so I've got a pair of sides for these two triangles. Let's see, what else do I know? Don't I know that R is the same value? All radii are congruent, and so these two segments are congruent. So I've got another pair of sides. What else do I know about these triangles? Specifically, what do I know about this radii at the point of tangency? Well, the radii is perpendicular at the point of tangency to the tangent. So that's a right angle. The same is true for this angle at angle A. And so I've got a right angle. It looks like this is a hypotenuse, right? That is congruent. This side was a hypotenuse. And it looks like R is a leg. So really I have HL going on here because I have a right triangle, right? I've shown that I have a right triangle and I have the hypotenuse congruent. I have a leg congruent. So by HL, these two triangles are congruent, which means all their parts are congruent, CPCTC, which means that these two green lines are congruent. So that's just proof that the 2-tan theorem is correct. You will use the 2-tan theorem in proofs, yes, but also in find problems, okay? All right, so a couple example problems for you. Take a look at this problem. So it's given that TP is a tangent line, all right? It's also given that TP's value is 8, all right? I'm gonna write an 8 there. I know that this O is the center of a circle with a diameter of 12. And so if the diameter is 12, that means that this radius here is 6, right? So we have to find OP. The reason why we can find OP is because we were given, the reason why we can find OP is because we were given this piece of information. TP is a tangent line. If it's a tangent line, that means that TP is perpendicular to the radius, which means we have a right triangle. So we can find OP either by using the Pythagorean theorem or by realizing that this is a special Pythagorean triple. It's a 3, 4, 5. 3, 4, 5, 3 times 2 is 6, 4 times 2 is 8, right? And so OP, if we realize that, hey, that's 3, 4, 5, then we'd know that OP is definitely 10. Or if you don't remember your special Pythagorean triples, you could just set up the Pythagorean theorem. A squared plus B squared, so let's see, 6 squared plus 8 squared equals OP squared. Okay, what is that? 36 plus 64 equals OP squared. And what do you get, 100 here? So that's OP squared. Take the square root of both sides. Looks like OP equals 10. So you could solve it either way. But the key is, if you've got a tangent line, you know that there's a right angle there. Another type of problem is what the book calls a walk-around problem. And here's why. Let me just show you the setup first, all right? What's given? You know that BC here, CD, DA, and AB, you know they're all tangent lines, which means that all of these points here are points of tangency, right? Points of tangency. And, well, what else do we know? We know that AB is 10, okay? So this whole value AB is 10, all right? Let me just indicate that. Excellent. BC is 15, okay, let me indicate that. BC is 15. And AD here is 18, all right. So we know some information. Let's see, what else do we know? Oh, well, we gotta find CD. So we need to find this value here, right? CD. And this may seem very daunting. You need to think about what type of information you know. You remember the 2 tan theorem? 2 tan theorem. It says that if two tangent lines or segments meet at an external point, then those two segments are congruent. Which means that, let's see, well, it means that EB here is congruent to B, whatever that point is, right? These are two tangent lines. Might be hard to see. These are two tangent lines. They meet at an external point, which means they're congruent by the 2 tan theorem. Oh, the same thing is true about AE here and A, whatever that point is. These two segments are congruent by the 2 tan theorem as well. These two are also congruent, 2 tan theorem. These two are also congruent. So you have some information that you could use. The trick to solving this problem is to start, I like to start with the thing that I'm trying to solve. You could either start with this piece of CD or this little piece of CD. So I'm trying to solve for CD here, so I'm going to start here. They call it a walk-around problem is because you start by saying that this little segment is some value. Let's call it X. We don't know what it is exactly, but we know that we can call this segment X. Am I right? Which means that if that's X, then that's X. Okay, then this little segment is X as well. All right? And we're talking about these two segments. So if that's X, then that's X. Now there's a relationship going on. If the total here is 18, and this is X, then this tangent segment is going to be the total minus X, right? So this little piece is 18 minus X. So you start somewhere, you say what it's congruent to, call it the same thing, and then you work your way around, you walk around. If that's X, that's 18 minus X. And if that's 18 minus X, then this is 18 minus X as well, because they're congruent. Now, this would be 10 minus 18 minus X. Now, what you're going to have to do is you're going to have to work this out, because if you don't write 10 minus this in parentheses, 18 minus X, then you'll probably forget to distribute the negative and you're going to get it wrong. Okay? So make sure you write it down, distribute the negative. This is really 10 minus 18 plus X, right? Combine, what is that, like negative 8 plus X, and for the sake of simplicity, let me call it X minus 8. It's the same thing, right? So this little segment here is really X minus 8. Let me recap for you. We start at one spot. One of the spots on the unknown that we're trying to solve for, this whole side here. We could call this X. We don't know what it is yet, but there's a relationship. Since these are both tangent lines that meet an external point, they're congruent. So if that's X, that's X. And if this whole thing's 18, this is 18 minus X. Make sure you put the 18 first, minus this little piece X. So this side, this segment here, 18 minus X, and these are congruent, so that's 18 minus X. Then you take 10 minus that. Make sure you distribute to get that this segment is X minus 8. This is a big system that we're working with here, and they all have some things related to them, that we're relating X to every piece. And so if that's X minus 8, then this is X minus 8. Hopefully you can read that. And if this whole thing is 15, then this thing is, well, let's do it off to the side. 15 minus that little piece, so minus X minus 8. Distribute your negative. So that's 15 minus X plus 8, which is really, what is that, 23 minus X? So this little piece here is really 23 minus X. 23 minus X. 23 minus X. And if these are congruent, then this is also 23 minus X. All right, you start at one point, you walk your way around it. Once you get back to the place you started, you can then write this down to say what CD equals. So we want to find CD. Well, CD equals X plus this piece, right? It equals X plus that piece, which is 23 minus X. Okay. All right, we could drop our parentheses. X minus X is just 0, right? Which means that CD equals 23. The X's drop out, thank God. So anyways, this is called a walk around problem. I believe problem 10 in your homework is like this. So here are 2 examples. Make sure if you have any questions, you post them in the discussion. I will post your homework in the assignment. Thank you. Bye-bye.